Welcome to A-Level Maths Topic by Topic. Today we're going to have a look how to get the differentials of sine, cos, ln and e to the x. I'm going to try and do them from first principles. Sometimes these come up as questions in the exam and they're not particularly nice. So let's go and have a look at how we go about doing this. Looking at how to do this differentiation from first principles, it's probably an idea to try and cast our minds on how to actually do any of these bits and pieces from first principles. So let's just remind ourselves about how we might try to look at differentiation from first principles of a simple curve. So let's have a simple curve here, and this is going to be some sort of function of x. It doesn't really matter what it's going to be. Now let's take a point on this line, and what differentiation is we're trying to work out the gradient. So I want to work out the gradient at that point there. And the way that we try to do this with differentiation is we look at another point and we gradually work out the slope of that point, and we gradually bring these closer and closer together until we get a tangent. So I'm going to choose another point on this line. I'm going to call it B. And what we're going to try to do with this is we're going to try to work out the gradient of this line. Now, to work out the gradient of a line, it's very easy. We know that the slope of AB here is simply going to be the rise over the run. And so this is what we're going to do. Let's take this point A here, and this, we're going to give it a position, and we're going to say it's going to have an x coordinate. And to work out what this line is, the y line here, this is going to be basically some function of x. So we've got this coordinate. Now let's take a very small distance along here. And this very small distance along here, we're going to define as delta x. I drew my delta around the wrong way. So we've got a delta x, a small distance here. Okay. The coordinate of this point is going to be x plus, done round the right way, delta x. If we look at this point on this line here, this is going to be the same function of x plus the small little bit plus delta x. So we've now got enough information here to try and work out the gradient. The gradient here is simply going to be by us trying to draw in a nice right-angled triangle. And we know this distance here, and we know this distance here, because this distance is going to be the larger distance, which is here f x plus delta x minus the short distance f of x. And so we can work out now the slope of the line and that slope of that line, or our gradient, is going to be our rise divided by the run, which here is going to be delta x. Now, what we do is we start bringing those points in closer and closer until we can get the gradient of the line, and that is going to be as we approach the limit, as delta x is going to tend to 0, of this distance called delta y over delta x, which is the same as the limit as delta x approaches 0 of this f x plus delta x plus f of x over delta x. So this I've done in more detail in one of my other videos, but we've got here a definition of what we've got for differentiation. So let's see where we're going to start. Now, I want to start now looking at sine. And if we're going to try and differentiate sine, then we need to know various things. That was the first one. Now, we'll give that a number. There is number 1. The second thing that I need to know is that if I've got sine A minus sine B, and I'll work this out in a previous lesson, this is going to be 2 cos of A plus B over 2 times the sine of A minus B over 2. So one of our trigonometrical identities. Let's have another one. Might be useful. We'll remind ourselves that cos of A minus the cos of B, this is going to be minus 2 the sine of A plus B divided by 2 times the sine of A minus B over 2. So there's a couple of trigonometrical identities, which in fact I proved in a previous lesson. Let's now take another fact. And this one I think we're going to need to try and prove. And here I want to look at the sine of theta divided by theta. We're going to measure theta is going to be measured here in radians. We're going to find that as theta here tends to 0, then we're going to see that sine theta over theta will tend to 1. So if we write that, the limit of theta approaching 0, we're going to find of sine theta over theta is going to become equal to 1. I think we need to try and prove this. So let's see if we can draw out a little table to do this. Let's take theta, which is measured in radians, and we're going to work out what sine theta is going to be, and we'll work out what sine theta over theta is going to be. So we'll set theta here to 1 radian. And if we look up the sine of 1 radian, we'll see that this is 0.84147. So on. If we then divide that by 1, this is going to be 0.84147. Let's now take a much smaller number for theta. Let's look up 0.1. And looking up 0.1, the sine of 0.1 theta in radians is going to be 0.09983. And if I divide that then by 0.1, we're going to get 0.9983 and so on. Let's tend this more towards 0. So let's go for an even smaller value of theta measured in radians. And this is going to be, the sine of that is going to be 0.0099983. Divide by that, it's going to give us 0.99983. We can see that as this tends towards 0, this number here is tending towards 1. So that's our next little fact that we need to know when we're going to try and do this differentiation of sine. Okay, now we've done that. Let's just do one more thing here, just to try and give us some ideas about what's going on. So let's look at the function of sine itself. So let's just draw in a little sine curve. Not one of my better ones. Here we've got 0, 90, 180, 270, and 360. When we're looking at differentiation, we're looking at here the change in gradient. We're looking at the change of the gradient. So let's see if we can plot here something about the gradient. If I look at 90, we can see that this gradient here is rather different. What we've got here is we've got a gradient of 0. So let's see if we can plot that on this graph. So that's going to be set at 0. And we can also see that when we've got 270, we've also got this set at 0. Let's look at a point 180 and let's see what's going on with 180. Well, at 180, we can see that the gradient here is at its maximum. And in fact, we know it is here at 1. It's going down in this direction, so we know this gradient is -1. If we look at this point here, 0, again, this is going to be at 1. And we look at 360, and now the gradient is positive. At its maximum, it's going at 1. Let's just draw this one in. We haven't plotted all the other points, but if we were to try and do this, we would see that we've got something which is approaching a cos curve. And so by looking at the gradient of this sine, we can see that it has become a cos. So we are seeing that if we do some sort of function, y or equals some sort of function here, which is sine x, when we differentiate this dy by dx, we're going to get cos x. So we've got here some facts that we've done. We've done here a differential. We've got some sine and cos rules. And we know that sine theta over theta is going to tend to 1. And we know where we're going. So let's now see if we can try to do this from scratch and see if we can work out what goes on when we differentiate sine. So let's see what we can do. I've got some function of x, and this is going to be sine x. We're going to try and work out here our differential, and we know from playing around with our differential that we're going to take a small increment of our sine x. So we can say that if we've got a function plus a small amount of that function, and then that's going to be the same as taking sine of x plus a small bit of x. When we met our differential, we found that we had the rise part of this as this equation here. So let's try that with my sine, and we're just going to say simply that we had f of x plus delta x minus the function of x. Well, if we relate that to the sine and put sine in there, this is going to be the sine of x plus delta x minus the sine of x. Looking at this, this is one of those sine functions that we looked at earlier. We noticed the sine of a minus b. So this is in the form of sine of a here minus b, sine a minus b, or we could write that as sine a minus the sine of b. Makes very little difference here. So what is that? Well, we know that fact, so let's rewrite this in the form of this answer, which is here to say that the sine of x plus delta x minus the sine of x, this is going to equal 2 cos of here, it's going to be x plus delta x plus x all over 2 times the sine of here, it's going to be a minus b, which is going to give us here just simply the sine of delta x over 2. Let's see if we can tidy this up a little bit. So that's going to be 2 cos 2x plus delta x all divided by 2 sine of delta x over 2. Let's do a little bit more tidying up, and let's split this. And I'm splitting this because I know where I'm going here. 2 cos, this is going to be x plus delta x over 2 times the sine of delta x over 2. Let's now try and look at the differential of this. So what we can do is look at this factor here of 2. Let's, rather than multiply everything out by 2, let's do the opposite. Let's going to divide it by 2. And let's look at our differential. Our function for our differential here is going to be dy by dx is going to be here, as we approach the limit of delta x approaching 0, we know that our function is going to be x plus delta x minus the function of x, all divided by delta x. We've already worked out some of these bits and pieces. We've worked out that this function is going to be that one. So let's put that in here, which is going to give us here the limit as delta x approaches 0 of 2 cos x plus delta x over 2 times the sine of here delta x over 2. All over delta x. What I'm going to do is I'm going to now divide by 2. Rather than multiply this by 2, I'm actually going to divide this by 2. So, leaving that one up the top so we can see what's going on, let's just divide this one by 2. So, the limit of delta x as it approaches 0 of cos x plus delta x over 2 times sine of delta x over 2 all over delta x divided by 2. Well, looks like we've got a mess, but in fact we usually find that when we start to get these sort of messes, we can normally resolve things. So let's see if we can just simplify this a little bit more. So what I'm going to do here is I'm just going to split this fraction. So the limit of delta x approaching 0, we're going to now have cos of x plus delta x over 2 multiplied by the sine of delta x over 2 over delta x over 2. As delta x tends to 0, we can see that, hopefully, that the limit as delta x tends to 0 of this sine of delta x over 2 over delta x over 2 is very, very similar to sine theta over theta, where we just can say here that our delta x over 2 could equal theta, and so this tends to 1. So let's rewrite that as it tends to 0, as see what happens. So we've got then the limit of delta x tending to 0, and we've got here my cos of x plus delta x over 2, and that's just going to be 1, and this delta x is also tending to become 0, so this is now becoming a very, very, very small number, and so this will become just equal to cos x. So therefore dy by dx is going to be of sine is going to be cos x. And there we've proved it. This is the differentiation of cos x by first principles. That's the first one. Now, shall we have a look at the second one? Let's see if we can do what we did with the sine, and can we do that with cos as well? And this is not really any different than we had before. We've still got our same facts that we knew, and because we know of all of these facts of differentiating of this cos function of sine approaching 1, then we should be able to work out and differentiate cos x. So let's see if we can try and differentiate now cos x. So let's start with our function. So my function of x here equals, this time, cos x. So if we've got f of x is cos x, so that we know that some sort of function of x plus delta x will also equal the cos of x plus delta x. We also can work on the idea that then f plus delta x minus f of x is also going to equal cos of x plus delta x minus the cos of x. Okay, so we've worked out that. Now, what else do we know? We know our cos function. We know that the cos of A minus the cos of B, just to remind you, is minus 2 sine of A plus B over 2 times the sine of A minus B over 2. So let's see if we can write this in an alternate form. So we've got cos of x plus delta x minus cos x is going to be the same as minus 2 sine of x plus delta x plus x, all divided by 2, times the sine of, take them away, delta x over 2. We can do a bit of tidying up here. Minus 2 sine of, we're going to get 2x plus delta x over 2 sine of delta x over 2. We can see this is going the same way as we did with the sine. So let's rewrite this as minus 2 the sine of x plus delta x over 2 times the sine of delta x over 2. Using our definition of the derivative, so we've got dy by dx. This is going to be as we approach the limit of delta x approaching 0. We know this is our function of x plus delta x minus the f of x, all divided by delta x. Let's substitute that into there. So as we approach the limit of delta x approaching 0, we get minus 2 sine x plus delta x over 2 sine of delta x over 2 all over delta x. We can do the same as we did before with our dividing by 2. And I'll just write that out in full for you. So we've got the limit as delta x approaches 0 of here. It's just going to now be minus sine x plus delta x over 2 sine of delta x over 2, all divided by delta x divided by 2. As we split the other one, so we're going to split this one. So we know again that as we get the limit of delta x approaching 0, we're going to get minus here sine of x plus delta x over 2 times the sine of delta x over 2 all over delta x over 2. We're knowing that delta x is tending to 0, and so as before, we had this limit as delta x tends to 0 of our sine delta x over 2 over delta x over 2. That is going to tend to 1. So this becomes 1. And as it becomes 1, so the limit of delta x tending to 0 is now going to be minus sine of x plus delta x over 2. And as this is going to approach 0, therefore that's going to become insignificant. So it's going to be minus sine of x. Therefore, dy by dx here is going to equal minus sine x. So we've used a differentiation here from first principles to find the derivatives of the function sine x and cos x. Okay. Now, the ones that most people really don't like, and we're going to have a look at the logarithm ones. We're going to look at this nasty thing called ln. Basically, we're going to try and have a look at how we're going to differentiate some sort of function of x that's going to be ln x. So we're going to try and work out how to differentiate this function, and we're going to try and work out e to the x as well from first principles. But to do this, we've got to try and understand what is e. And I find that people do not really understand what e is. So let's have a look at what e is. So let's take a particular function. And the function I want to look at is 1 plus a number to the power of 1 over that number. And what we're going to have a look at is seeing if we can take this to the limit as t approaches 0 for 1 plus t all over to the power of, 1 over t. Let's have a look at this function. Let's see what happens. I'm going to have my values of t, and we're going to start off with 1, and we're going to look at 1 plus t to the power of 1 over t. Well, for the first one, this is going to be really quite easy. This is going to be 1 plus 1 to the power of 1 over 1. This is going to give me 2 to the power of 1, and we can work out that's going to be 2. We're going to get t, and we're going to tend that to 0. So let's take t as a much smaller number, 0.1. This is going to be 1 plus 0.1 to the power of 1 over 0.1. For this, we need to put it into the calculator, and the calculator comes out with 2.594 and so on. Let's make t smaller, 0.01. 1 plus 0.01 to the power of 1 over 0.01. We put this into the calculator and we get 2.7049. Let's make this smaller still. 1 plus 0.001 to the power of 1 over. And as we put this into the calculator, we get 2.717. Let's do it a final time. 1 plus 0.1231 to the power of 0.1231. And this becomes 2.718 and so on. Now, this number here is the value E. So we've got a feel for this, that as this t tends towards 0, then this number here is going to tend towards E. So this exponential constant. So let's write our summary down here, that the limit as t approaches 0 for the function 1 plus t to the power of 1 over t is going to tend towards E. And this is a very important key result for us. Now we've got that, let's just see if we can go and put in some more important facts before we start doing our differentiation. So let's try and put these in.
This is a reminder. Take a written tablets.
Right, just silence my Alexa device, which is trying to help me. Right, okay. So let's put down our key results. We've just had our first one here, and our first one is that the limit of t approaching 0 of 1 plus t to the power of 1 over t is equal to E. Let's look at our differential one. So to look at our differential, of our equation. So we know that the limit of as delta x approaches 0 is going to be our function of x plus delta x minus our function of x, all divided by delta x. And that's our second thing we need to know. We also need to know something about logs to do this differential. And we need to know that the log of A minus the log of B can also be written as the log of A divided by B. The fourth thing I need to know is that if I have a log written as M log of A, I can write that in the form of log A to the power of M. And the fifth thing I need to know, that the log to the base E equals 1. So that gives me my basic functions so that I can actually now try to differentiate my ln. So we're going to have here those ideas in our mind, and we're going to work out f of x of ln x. We know, using our function of the derivative, that f of x plus delta x minus f of x all over delta x. We could write that with our ln here. So we've got ln of x plus delta x minus ln x all over delta x. This is here the same as taking away 2 logs. So we can see if we can write this as one log function. So if I just look at the right hand of the equation, we're going to say that 1 over dx of ln x plus delta x minus ln x, I could write that as 1 over delta x. Didn't do a nice delta there, did I? Of the ln of 1 over the other one. So this is going to be x plus delta x over x. And if I divide these ones, then 1 over delta x ln of 1 plus delta x over x. Now, in order to try and make this a little bit easier, I think I'm going to need to try and make my life a little bit easier. And let's say that I set a variable t, and t is going to equal delta x over x. And we could rewrite that by saying, well, that delta x is going to be equal to x times t. This is basically going to be done so I can do the calculations and we can work it out a little bit easier. What happens if x becomes 0? Well, I'm not going to worry about that at the moment because we're really interested in differentiating ln x rather than worrying about this. So we're going to just assume here we're going to have positive values of x. So if that's going to be true, then we can say that for my function here, f of x plus delta x minus f of x all over delta x could be written as 1 over x t ln of 1 plus t, doing my little bit of substitution. Now, remember our rule that we had m log a is the same as log of a to the m. So we can also be aware of the fact that 1 over xt is the same as 1 over x times 1 over t. I find students find that one the harder of the two. They're not very good at fractions. So let's now see if we can rewrite this. So using this here, we'll see if we can try and rewrite this to make life easier for us. And let's write this out as going to have here of my f of x plus delta x minus f of x all over delta x could be written as 1 over x ln of here 1 plus t to the 1 over t. And that looks familiar here, because what we've actually done there is we've looked at here this sort of idea that as delta x tends to 0, and because of that, t is also going to tend to 0. So when we're looking at our derivative, our f prime here, we've got the limit as, in this case, t tends to 0 of this 1 over x of ln 1 plus t to the 1 over t. So as that is approaching, we know that one plus t to the 1 over t is going to tend to e. So this then becomes 1 over x ln e. Now, we also know that ln of E here equals 1. So our derivative dy by dx of my function of x of ln x becomes 1 over x. And we've managed to show from first principles and show that's true. We're left with one final one to try and work out, and this is in fact quite a lot simpler to do now we've actually done that. So bearing all of ln x in mind, let's see if we can now do the same thing but for e to the x. So let's see if we can simply differentiate here from first principles e to the power of x. To try and differentiate this function, which I could write as something like y equals e to the x, then I could, because we know of our different ways of writing logarithms, we know that a equals, if you like, b to the power of c. That could be written as the log of b to the of a equals c. So we know that. So if I do the same with y equals e to the x, then I could write that as log e of y equals x, and we tend to write that as ln y equals x. Okay, so there's a couple of things we know. If I differentiate, then this ln y equals x, then I'm basically doing d over dx of ln y, and we know that's going to equal 1. So we want to try and find out dy by dx. Now, what you should know from things like the chain rule that dy by dx equals simply here dy by du times du by dx. There's our familiar chain rule. If we write that in this form, then we're going to get d of dx, isn't it, of ln y, that's going to equal d of over dy ln y times dy by dx. So there's our chain rule. So we also know that we've worked out most of that. So we should know that if I do a d of dy of ln y, that's going to equal 1 over y, because we've just gone through and proved that. Let's rearrange this so I know that 1 over y times dy by dx is going to equal 1. If I rearrange this, then I can see that dy by dx is going to equal y. But we said right at the beginning that y equals e to the x. So we know that if we've got some sort of function of x where it equals e to the power of x, then the derivative of this is also going to be e to the x. And this is this peculiar thing about this number, that when you differentiate this number, then you get the same result. So it's been quite a bit of heavy stuff trying to go through that, but they are things that do come up in the exams. They do come up of trying to get you to work out from first principles. And you can see that they follow a logical pattern, that differentiating sine and cos are done in exactly the same way, of knowing some extra facts and bringing those in. There's no real way of trying to do those from scratch unless you've practiced doing them. And once you've practiced doing them a few times, then they become relatively easy and second nature. And you start to understand how all of these things that you've been learning about logs, about trig, all work into differentiation, and how they also work into integration. Because to solve some integration, the only way to do it, as we know, is to learn to differentiate, as Isaac Newton discovered. With that idea in mind, I will leave you, and I will see you probably next week. If you liked what you saw, please then subscribe. Stay safe, and I'll see you next week. Thanks for watching. Bye-bye.